Good morning, students. Welcome back. So, this is the third lecture of the Unit 1. So, today we will be studying about the behavior of the MOS channel, and also we will look into the IV characteristics of a MOS device. Right? So, before that, as we have already studied about the MOS structure, right? About the MOS structure means here what all it consists of, the device structure like a gate, the metal gate or a polysilicon gate, the oxide layer as well as the substrate, right? Forming a metal oxide semiconductor, right? So before that, we need to study what the channel is, how the like the transportation of electrons in the channel take part, and what are its voltages that to conduct. So those points we will be going through today. So before that, so first we will look into the behavior of the channel. First, what is channel, how it is behaving with applied voltages, and how the electrons flow into the channel. Those points we will go through. So this is a MOS device, N plus. This is for the say this is a source, and again this is N plus. This is said as drain, and this is oxide layer, and this is polysilicon gate. Okay, this is gate, and we say that, and this is a substrate, right? P substrate, right? We know that from the theory of the Mosfet, we studied that the channel formation will actually happen in this, right? In this area, we know that there is a channel formation. Channel formation means what? The movement of electrons with the movement of electrons from source to drain with the applied gate voltage. And what is gate? Where it controls the flow of electrons in the channel. Okay, it simply controls the current in the device, or electrons in the device. So case 1, first is here we will be looking into two cases. Okay, first, okay, we'll be going through with two case. First is case 1. Case 1 is that VGS, okay, VGS is greater than VTH, okay, but VS e- but Vs and Vd equal to 0. Okay, case 1 is that we are saying that VGS, the applied gate voltage, is greater than the threshold voltage. Okay, that means in this case, that means the device is on. Okay, the device is said as on. If it is on, that means there is a conduction taking part in the device. Is it that? So that we will look into. Okay, and said that VD and VS and VD equal to 0. That means both have same voltage. That is 0 voltage. But the gate voltage is now connected to some battery. Okay. Here is plus minus some battery source as applied to the gate voltage. So now here we need to understand that what is the density of electrons across this. As we said, it is a channel, right? Now these electrons need to move from source to drain. So now what is the density of the electrons across this, right? So that we need to understand. We said that the device is on, but has no current. Okay, but has no current, because in order to conduct, or in order to generate current in the channel, there should be a voltage difference between the source and drain, but we have a equal voltages, and here we say that it is a resistive path. Okay, this is the resistive path where the current will actually takes place. So now we should know that what is the current density or electron density. So it is very clear that the device is on, but whatever the density of electrons are same. That means the charge is same along the channel. Okay, the charge is same along the channel. This is case 1. Coming to the case 2. Case 2, uh, let me draw quickly the MOS structure. Okay. Okay. Again, this is N plus P sub, that means P substrate, oxide, right? This is gate. Okay. VG. Now, the case 2, the condition 2 is that VGS is greater than VTH. Okay. But Vs is equal to 0 and Vd is also greater than 0. Okay. We haven't said that Vd is greater than 0. We only said we are looking into the behavior that's saying that VGS is greater than VTH. That means the device is on. Okay, the device is on, but Vs is 0. So this is 0. Vs equal to 0. Here it is greater than VTH. Okay, and this is Vd is now greater than 0. Right? Now, again, the same scenario, we know that the electrons occupy at this region, right? Free electrons accumulate at this area between the source and drain and have a voltage difference and have the current. Okay, and the positive current, here the positive current is now flowing from this to this ID. Sorry, the current is now flowing from here to here in this direction, from from here to here the current is now flowing. So if we observe that the current is flowing, then one thing we need to understand that what about the current density again. As we know, there is again a current flowing through this resistive path, right? The current will be flowing through this resistive path. And one thing here we need to observe that here this is one plate. Okay, this is plates to form a capacitor. Okay, the channel voltage also varies because the channel voltage because why the channel voltage is now varying, because here here it is 0, here the source voltage is 0, and here but the drain voltage is greater than 0. So there will be a difference, there is a change in the channel voltage. But one thing here we need to see that we need to observe that what about the density, because assume here I'm giving here the voltage, assume the gate voltage is something 1 volt. Okay, we are, yes, in case 2 we said that sorry, VGS is, in case 2 we said that VGS is greater than VTH, right? And Vs is equal to 0, and Vd is also greater than 0, right? Vs is equal to 0 and Vd is greater than 0, right? This is case 2. Case 2. So here we saw, like, suppose assume if we are giving a gate voltage if it is equal to 1. Okay, just a minute. It is Vg. Okay. Now Vg is equal to 1, and assume here, this is our assumptions, Vs is equal to 0.5 volt, assume. So now if I draw a MOS transistor, okay, this is n plus, somewhere channel is here, P sub, Vg, Vd and Vs. Okay, this is oxide and this is gate, polysilicon gate, and Vg is equal to 1 volt, Vd is greater than 0, Vs is equal to 0. So this is what we have given. So now we said that a positive current is flowing here. This is ID, and we have what do you call? We are saying, like, there is a voltage difference. The device is on, right? The device is on. There is a voltage difference, and we say that there is a change in the channel voltage, right? Because here the channel voltage, it will be something 0 at this point, correct? At this point the channel voltage is 0, this point, and again at this point it is something different, correct? At this point again it is different, again here it is different, means along the channel the voltage is varying, but when it reaches here, we can observe that when it reaches here, the voltage here would be 0.5 volt across here at this end, but at this end the voltage would be 0 volt, because this is respective with source and this is respective to drain voltage, right? Suppose if I want to find it out the voltage across here, okay, if I want to find it out the voltage across here, so we can have a difference, like gate voltage is 1, right? 1 minus something 1 minus 0.5, right? Something we see here, the voltage is of 0.5 volt, right? This one, this voltage is observed somewhere over here, right? So now in this case, then what about who is acting this, who is making to do this? Because this is something like we are wearing, we have observed a change in the voltage across the channel. So this is all because we say we have a resistive path. Then what about the capacitance? Who is playing? Is that the general capacitance that is sorry, acting a part, but not actually the general capacitance, it is a local capacitance. So therefore the capacitance will be high over here and the capacitance will be low across this, right? So here the capacitance is low and the capacitance is high. So as we come across again here, assume that something 1 minus 0.2, right? It will be something 0.7, or as sorry 0. Or point 1 or point 0.2 something, if we calculate, then there will be a voltage difference. So here, once you reach here, it will be 0.5 volt. Okay. Uh, as we know that Q equal to CV, okay, when this is happening, when this is actually taking part, then we are saying that the Q and the V are small. Okay, the charge and the voltage is small in this case because of the local capacitance that is involved across this area. Okay. In general, we say that metal MOS is also a, we say MOS capacitor, right? This is a metal, then oxide, then again metal, something like. But in this case, we have a semiconductor. But still, we say this capacitance is high over here and low over here, but we have a charge and the voltages are small because of the local capacitance. Okay. Local capacitance. So now this is what we are looking the, this is what we have understood the behavior of the channel. Third is something we have the dimensions of MOSFET. Okay. The dimensions. Dimensions of MOSFET. So this we will look into. So here in this reflections part, just now we were discussing about the dimensions of MOSFET, right? Dimensions of MOSFET, right? First thing, why should we consider why should we consider this dimensions? What the parameters that are included for the MOSFET? Okay, why we are first point is why we are using these dimensions. Okay, because one thing is very clear that considering these dimensions, deriving we will be deriving IV characteristics of MOSFET. Okay, we will be deriving IV characteristics of MOSFET. So here I have a question to you. What all the parameters? What exactly? Not exactly, or you can just I mean it's a type of brainstorming. You can just think of what all the parameters that we will consider for deriving the current voltage characteristics of MOSFET. So what I do, I'll give you 60 seconds just to think of it. What are the various parameters? Okay, that with respect to two dimensions, okay, that we will be considering for the derivation. So we will be back after 60 seconds. So yes, so what we were doing, we were discussing about the dimensions. So let me draw here a MOS device. Okay. Uh, it is bit difficult to draw, but it's okay. Right, something like this. So here I'm showing you the cross-sectional view, the 3D, sorry, 3D view, right? And here it is oxide. This is gate. This is oxide, and here somewhere we have a gate contact. Okay, here I have a gate contact, and this is for source and drain, right? Okay, this is for the n plus this source and drain. Okay, and now we say like this is gate, right? This is gate, and here it is a oxide, right? And sorry, and that is obvious. You know that here there is a channel. So from this dimensions, what we will be observing? First is we will be looking at the sorry, what you call gate. Okay, we will be looking to the channel length. Okay, we will looking to the channel length. Okay, length of the channel, then the width of the gate or the length of the gate, thickness of the oxide, right? TOX and etc. Okay, these are the dimensions of the device where we will mainly these are used for the deriving the IV. Okay, current voltage characteristic. So now if I want to say, I can simply say that this is the length of the channel, right? This we say that channel length. Okay, this I say that as L, and this we say the width of the gate. This I say like this is the width of the gate W, and here is the oxide thickness, right? This one is the oxide thickness, that is TOX, correct? So I am done with this and this, right? One thing, if suppose if I am a circuit designer, then I have the option of wearing this, or I can take, or I can design any circuit by changing the length and the width of the gate. Okay, I can change, I being a circuit designer, I can change the length and the width of the gate. Okay, sorry, yes, this is width, length and the width of the gate. I can vary, but the oxide thickness is not in my hand to change the dimension of the oxide thickness. Okay, because here in order to change this W by L, you have a aspect ratio. Okay, aspect ratio, that is said as W by L, where you have the option of varying or changing it. Okay, you can change this. You can change this aspect ratio. But the TOX, whatever we are saying, the oxide thickness, TOX, this is not in the hand of a designer. This is not in the hand of the designer, that where we can vary or change the thickness, because this is fixed and it is given by the foundry. It will be given by the foundry, because when I want to design a layout, in order to design my layout, I can change the width and the length, but there is no possible way for me to change the oxide thickness. Okay, because the library, whatever it is defined for the oxide, that I need to consider, and accordingly I need to design the layout design. So next is one more thing. So next here, as you saw that it is a device, right? A three-dimensional device I have shown just now, right? And something like this, you have oxide, right? And drain, right? This is n plus p sub the source, gate, and drain, right? So this is, we saw something 3D, and this is said as W, and this is said as TOX, the oxide thickness. And one interesting part here, we say that this is length of the channel or gate of the channel, whatever, with whichever notation, if you want, we can use that. Okay, that is not a thing. But here interesting thing is that this actually this the source end and the drain end will not actually start from here. It will start somewhere, something like this. Okay, and here it will start somewhere, something like this. Why? Because you have some things that it is moving at this end. Okay, some why? Because while doing a process flow or the fabrication process, okay, while doing a fabrication process, we have studied about the implantation, right? Implantation and diffusion, right? Diffusion, like we have come across the terms implantation and the diffusion. This what happens when we were trying to implant it to form the source and drain regions. Okay, this will, and after implanting it, this will be heated. The chip is raised to heat. Okay, after implantation, the chip is raised to heat, where it is set as thermal heating. Okay, thermal heating. Okay, due to this, the n type will now diffuse at this part. Okay, therefore the length will, whatever we have defined the length from here to here, this will be now said as an effective length. Okay, this is now said as LEFF, effective length. The distance from here to here, whatever we say. Okay, after the thermal heat, after the it get diffused towards here. Okay, when it get diffused here and here, then that distance we say it is a effective length. So while we are deriving it, we usually use this effective length. Rather using this length, we use this effective length. Okay, so I hope you understood for what purpose we are taking these dimensions, and these dimensions further we will be calculating or we will be deriving the characteristics. So with this you have understood the oxide thickness, and we will be considering the gate okay, width of the gate, and then rather we take the length of the device or length of the channel, we will be considering L effective, that is effective length. Why this effective length is happened? Because while we are doing the implantation for the source and drain, after implanting the chip is undergone with the thermal heating. Once the chip is made with the thermal heating, then these dopants, whatever we have doped here, that will start diffusing it towards here like this and towards like this. So therefore the channel will get the channel will be closer, and that length we will be considering, and then we say that it is an effective length. Okay, so we know why we have studied here what are the dimensions of the MOS device. Okay, thank you.